we are going to discuss phosphazenes. We all know by this time that the among P block elements, particularly second row elements, carbon has the highest tendency to undergo self, polymerization, which we call in a technical language catenation. And nitrogen and other elements, oxygen, they have virtually no tendency to show the catenation, probably because of the presence of the lone pairs, and therefore that creates sort of repulsion between these nitrogen or oxygen atoms, and therefore the tendency to form polymeric chains is curtailed to a large extent. The longest chain which is seen for nitrogen is azide, three-membered chain, which is very unstable compound. It very reacts very uh, easily, and by and large, in every reaction, the byproduct is molecular nitrogen is given off. So it's a reactive compound. Though same is the case of phosphorus to some extent, does show the tendency to undergo polymerization, and not with itself, but with the elements of the group second, phosphorus nitrogen, phosphorus oxygen. We saw in the case of phosphates, we can have polymeric chains, long chains, and cyclic chains. Also, the phosphates can condense and form the long chains, and that is attributed to the exceptional stability of phosphorus oxygen and phosphorus nitrogen bonds because of the 3D by P by bonding. So phosphorus and nitrogen also combine to form long chain polymeric compounds, and the monomeric compound is to some extent very is similar to the organic cyanides, nitriles. Just as carbon atom forms nitriles, R, C, triple bond N. In the same fashion, phosphorus also can form phosphorus divalent P, R2, uh, and triple bond N. That sort of compound, this monomer was called phosphazene. And therefore the name goes phosphazenes from that compound, also known as phosphonitriles. This we have organic nitriles, we have phosphonitriles, where you have sort of phosphorus nitrogen, triple bond. But this is monomer, which is very unstable and not so well established. And but when this phosphorus nitrogen bond replicates itself, forms a polymeric or cyclic compounds, then this situation becomes very interesting, and we have large compounds with special properties, like rubber-like properties, polymers, elastomers, and compounds which have multiple applications in diverse field, medical, biomedical applications, and industry also. These phosphazenes are exceptionally stable, and their elasticity is quite remarkable, in the sense that they are not they are fireproof, they are waterproof, and they're not affected by any solvent, and they are stable. They retain their elasticity at very low temperatures. So they are used as greases and o-rings in the helicopters, which fly at high altitudes where the temperatures are very low. And the phosphazenes, because they do not lose their elasticity when the temperature goes down, therefore they find multiple applications. Similarly, they can be used as drug for drug delivery, particularly in the bones. They can be tuned to biodegrade, and then they repair the muscles, repair the bones, and themselves over a period of time they decompose, and therefore they have multiple applications in the biomedical field also. So let us go into the what are the structural details and the pattern of the reactivity of these compounds. Let's go to the slides. Right. So PCl5 is, you know, is extremely reactive towards basic reagents like water and amine. Not only ammonia, all amines. It reacts, quite, remarkably with water. It is very hygroscopic substance. It is, extremely sensitive to the moisture. Therefore, in the summer season when the humidity is very high, phosphorus pentachloride it has to be stored in an airtight bottles, otherwise it hydrolyzes immediately. So the reaction is very fast, and it gets converted into POCl3. That's the immediate product in the humid atmosphere. However, if the compound is allowed to react with water, excess of water, it is dissolved in water, then the ultimate product is the POCl3 again undergoes hydrolysis, and three water molecules displace the three OH groups. Initially, the OH water molecules displace the fluoro groups, and which undergoes hydrolysis, the dehydration, and then ultimate product is PO. In place of Cl, we have OH3, and this is nothing but orthophosphoric acid, which we were studying in the last lectures. So H3PO4. So that is the ultimate product of PCl5. It's a very reactive compound. So when you react this compound with ammonia, the product which is expected on the lines which is on the pattern of the reactivity with water is PO bond will be formed, and P double bond N bond will be formed because nitrogen is trivalent. So one hydrogen will be retained. So P double bond N and PCl3 will be formed. Or when the excess ammonia is used, Cl will be replaced by the ammonia, and then you will get the PNH3 thrice. So similarly, if you have a primary amine will also react in the same fashion, or the substituted amines will also react in the same fashion. But the characterization of these compounds was hampered due to one reason is that the compounds are very sensitive to the moisture, and the reaction was incomplete. It is a slow reaction, and difficulty in separation of the mixtures because of the air sensitivity of these compounds. There was difficulty in separating these mixtures. So moreover, gradual polymerization occurs with the loss of NH3 to yield phosphine, a poorly characterized solid with appropriate formula PNH2. This was proposed as a final product of the polymerization, and this was difficult to characterize because of its extreme reactivity and sensitivity to the moisture. But it was expected that its formula, molecular formula in a polymer should be PNH2. It is NH2, it is not N2H, it is PNH2 twice, right? So even the compound, this PNH2 monomer, P, H2 and then triple bond, and that will be called phosphazene. If instead of free ammonia, it's less reactive conjugate base, ammonium chloride, which is also an, its conjugate base of the ammonia, if this is used as an base as a compound, the reaction proceeds at a moderate rate and result is more definite. Ammonium chloride, when heated at 146 degrees, reflux, and the solvents which were used in this reaction historically was tetrachloroethane or chlorobenzene. These two solvents were used to avoid the water, and the compound was PnCl2. This compound was known as phosphazene, uh, polymeric compound. If the product is monomer, its structure is analogous to organic nitrile. So organic nitriles are or C triple bond N, and phosphazine is Cl2 P triple bond N. Therefore, the name goes phosphazine, and these are analogous to the organic nitriles. For the reason, original name is also called phosphonitriles because these are organic nitriles. We call them phosphonitriles. Phosphonitrile nitric chloride. This compound will be called phosphonitrile chloride. However, the products are actually either cyclic or linear polymers. There are two series of compounds that are formed by this process by this reaction of ammonium chloride with the PCl5 and tetrachloroethane or chlorobenzene. Either the compounds were long chain polymers or they were cyclic trimers, tetramers, pentamers, and hexamers up to the octamers. So, by analogy with benzene and borazine, these compounds became known as phosphazene because of the benzene and because the cyclic compounds were showing a sort of the aromatic character in the sense the pi bonds were not localized, they were delocalized, and the rings were having some aromatic character. The bond lengths were identical. Phosphorus nitrogen bonds were they were on the surface. It appeared that there were phosphorus nitrogen single and double bonds, but then when the structural details were developed, they found that all phosphorus nitrogen bonds are of equal length and strength, and therefore they resemble the benzene or borazine in that sense. So pi bond is not localized, it is delocalized. So with having some aromatic character, and therefore the name goes phosphazene. Major product of the reaction with ammonium chloride is a trimer. It's a cyclic compound, which is easiest to separate. This is the most stable compound. It is easy to separate, and there are three these molecules of this monomer in this ring, and the ring is hexagonal because there are 3 nitrogen and 3 phosphorus atoms at the corners of a flat hexagonal ring, just like benzene, and there is the phosphorus nitrogen bonds or somewhat between single bond and double. They are shorter than the single bond and longer than the double bond, indicating some sort of resonance in the ring. So a ring is flat hexagonal when n is equal to 3. The small amount of tetramer higher oligomers up to the n is equal to 8 have also been characterized. The ring compounds, the n goes, the size of the ring goes from n goes from 3 to 8. Bromo compounds were also prepared in the same fashion, where the starting material was not PCl5, but it was PBr5, with the only exceptional condition that you need to add excess of bromine because phosphorus pentabromide has tendency to undergo self-decomposition, and when excess of bromine is added, the reaction moves to the left, the equilibrium moves to the left. Therefore, the PBr5 is treated with ammonium bromide in presence of excess of bromine to check the decomposition of the phosphorus pentabromide so that you can form a trimer of the NpBr2. So in place of chloride, it is bromide now. So chlorides were not prepared directly because of the extreme reactivity of the fluoride. Phosphorus pentafluoride is not so stable. It's a very unstable compound. Therefore, they were prepared indirectly. First, the chloro compound was prepared, and then chloro compound was substituted with fluoride using sodium chloride as the substituting agent, and chlorine group got displaced by the fluoride, and you got LPF2 thrice. So that's the indirect synthesis of the fluoro compound, because the PF5 is extremely unstable compound. And for iro also, the PBI5 is also extremely unstable, and this was also the full iodo compound, NPI2. That compound is also very unstable, and by indirect substitution, just as fluoride compounds were prepared by indirect substitution, the iodo compounds were also tried, but they got only one iodo at one of the phosphorus atoms. If you have N3PCl2 at one phosphorus atoms, one alkyl group and one iodo group got introduced, and this is partially chloro. This is mixed chloro iodo compound. Pure iodo compound has not been able to separate. So this is halide trimer, planar 6-membered ring. This is the one compound where one of the phosphorus nitrogen bond is single bond, then alternate, then the next bond is double bond, then next one. So there are alternate single, double bond, bonds. Just as in the benzene, you have alternate single and double bonds between carbon and carbon. So here also the phosphorus nitrogen bonds, there are single bond, double bond, then single bond, double bond. I mean, this bond should have been here, a double bond. This is double bond here. So in the next structure, the bonds are shown in the different orientation. They are double bond and double bond. Just as benzene, you have the canonical structures. This is also the resonating structure of the dimer, of this trimer, cyclic trimer. Then if you have a straight chain compound, it has to be like this. Phosphorus has to be always pentavalent. So 3 single bond, PCl3, double bond N, and then PCl4, because phosphorus has to be pentavalent, 4 bonds this side and single bond this side. If you have the trimer, so this will be the NPCl2, which is the basic unit, which is the repeating unit in this cyclic compound, is NPCl2. NPCl2 is at the center. On the one side is PCl3, on the other side is NPCl4. So this remains the integral part of the all straight chain compounds. In the center will be repeating unit of NPCl2. See, this is one NPCl2, another unit of NPCl2. On the left side is PCl3, on the right side is NPCl4. So you go on adding, increasing the chain. The center will have, in the center we will have NPCl2, 3 units now. On the right side and left side, we have again PCl3 on this one side and NPCl4 on the other side. So for straight chain compounds, the end units are PCl3 and NPCl4. In between, you have NPCl2 repeating units. So that is the straight chain compounds. Now, this is another addition, another unit of NPCl2, 1, 2, 3, and then we have the same unit. Chlorine atoms are very reactive, and they can be easily replaced by different kinds of groups, alkyl groups, aryl groups, hydroxy groups, or alkoxy groups. Thiocyanates are substituted amines. So substitution is carried out either by Grignard reagents, magnesium alkyl compounds, or lithium alkyl compounds. So this is SH3 methyl magnesium iodide. You introduce methyl group. This is lithium, phenyl. You introduce phenyl group, and this is NaOR. You introduce alkoxy group, and sodium thiocyanate. You introduce thiocyanate group. So this is how the different substitutions are introduced in the phosphazenes, and different compounds with different physical properties and chemical properties are synthesized, right? So the substitution is also not so uniform, because if you look at the cyclic compound, there are this nitrogen atom is sp2 hybridized. It is forming, you know, one sigma bond on this side and one sigma bond on this side, and then using that lone pair of electron to form the d pi p pi bond, whereas phosphorus atom is sp3 hybridized, is forming four sigma bonds. So because phosphorus and nitrogen are on the same in the same group, the fifth bond phosphorus is forming is using its 3d orbital, and overlapping with the p orbital of the nitrogen atom, and through p pi d pi bonding, it is forming forming an pi bond. So the substitution is typical. One option is that if the two alkyl groups are displaced, both of them are displaced on same phosphorus atom, so that will be called gem dialkoxy. If the two alkyl groups. On the other hand, if one alkoxy group enters here and other enters at another phosphorus atom, then you have cis and trans isomers possible, depending upon whether because this phosphorus atom is tetrahedral, it is not sp2 hybridized, it is sp3 hybridized. One chlorine atom will be above the ring, one will be behind the ring. So if the chlorine atoms are displaced are on the same side of the ring, it will be called cis. If they are on the opposite side of the ring, they will be called trans. So there are three possible isomers in the case of in the substitution. Right. So this is known as phosphazene NPH2. If in place of Cl2 we have H2, this is known as phosphazene. And in the case of linear chain, this is the general formula: PCl4 on one side, NPCl3 on the other side, and NPCl2 at the center, repeating n times. It can be 1 time, 2 times, or 3 times, anything. So the tetramer, when you have 4 nitrogen atoms and 4 phosphorus atoms, there are two geometries. One is the chair form. It's a puckered ring. It's not a flat hexagonal flat ring now. It is puckered ring, and all atoms are not in the same plane. And this is the chair form, and this is the boat form. So you can see that every phosphorus atom is linked with 2 chloro groups, and nitrogen atom is not linked with substituents. I've not shown double bonds and single bonds here. Simple the structure. This is NPCl2 n times, where n is here 4. So the nitrogen phosphorus nitrogen bond angle is around 117, and phosphorus nitrogen phosphorus bond angle is much larger, 123, indicating that there is larger electron-electron repulsion at the nitrogen. When the nitrogen is at the center, the bonds are at the nitrogen atom being the central atom, and there is electron-electron repulsion is much less relaxed when phosphorus is at the center. So these are generally, the IUPAC name is polychlorophosphazene, phosphazenes. Poly means if there is this tetramer, we'll write tetrachlorophospazenes. If it's a trimer, we will call it trichlorophospazenes. Of course, cyclic word will be added if there is a cyclic compound. If it's a straight chain, then the cyclic word will be removed. So the pentamer has been found. This is tetramer puckered. Trimer was planar. Pentamer is again planar. So coming back to the trimer, the phosphorus nitrogen bond is 158 picometers, whereas phosphorus nitrogen single bond is around 1.97 or 77 picometers. So it is much shorter than regular phosphorus nitrogen single bond. So it is has some double bond character because of the p pi bond. So similarly, the bond angle between chloro phosphorus chloro is 108 only,
the bond angle between nitrogen, phosphorus, nitrogen is 180, and bond angle at phosphorus, nitrogen, phosphorus is 121. Again, indicating that there is significant repulsion, electron-electron repulsion at the nitrogen atom, bonding between the bonded pairs, and that is much less relaxed in the case of phosphorus atom, right? And also the fact that the lone pair on nitrogen is engaged in the uh, in the d pi bond. So phosphorus nitrogen single bond is 177 picometer, and phosphorus nitrogen in phosphazenes is in this range 156 to 160 picometer. So that it in fact indicates that there is some significant the double bond character in the phosphorus nitrogen bonds. And also what has been observed that phosphorus single bond and phosphorus nitrogen double bonds, they are equivalent. All bonds in the phosphorus nitrogen bonds in the phosphorus, this trimer, are equivalent. So if you write the canonical structure, this is single, then this is double. So both bonds have same length and strength, indicating that there is the phosphorus nitrogen bond is not localized, but it is delocalized. So no alternate phosphorus nitrogen single and double bonds. We have a delocalized p pi t pi bonding. So nitrogen is sp2 hybridized and phosphorus is sp3. 2pz of the nitrogen overlaps sidewise with 3dx and 3dy orbitals of the two neighboring phosphorus atoms simultaneously, forming a three-center pi bond. There has been a lot of controversy regarding the type of bonding, pi bonding we have in the phosphazenes. This is one of the theories which proposes that the pz unhybridized orbital of the phosphorus, which is pz, then that orbital overlaps sidewise with two neighbors, which involving 3dx and 3dxz and 3dyz orbitals of the phosphorus neighboring atoms. Hello, good morning. हाँ 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 बच्चे कहाँ पे हो आप? हेलो, हाँ हाँ तो हाँ हाँ अच्छा, तो हो गए होंगे तो आपका कितना मेरिट है? अच्छा, तो खत्म होगी तो फिर क्या करेंगे? आप कहीं बाहर कैंपस किसी कॉलेज में लेना चाहते हो एडमिशन? नहीं, वो मेरिट पे ही सीट देते हैं ना ऐसे। अगर आपसे ज्यादा मेरिट का कल आया होगा तो उसी को मिली होगी ना बच्चे। वो तो नहीं, कल एक्चुअली क्या होता है कि अगर खाली रहेगी तो वो आज भर जाती ना। तो अगर वो कल ही, क्योंकि उन्होंने कुछ मेरिट वालों को, ऊपर वाले मेरिट वाले एक ही दिन सबको नहीं बुलाते हैं। जैसे उन्होंने कल 70, जैसे हमारे यहाँ भी आज है तो हमने 70% तक वालों को आज बुलाया है। अगर आज खाली रह गई तो फिर कल 65 से लेके 70 वालों को कल बुलाएंगे। इस तरह के करते हैं ताकि एक ही दिन रश न पड़ जाए। तो उसमें कोई कुछ नहीं उसमें कुछ नहीं कर सकते बच्चे, वो क्या, क्योंकि मेरिट पे होती है ना एडमिशन। अगर मतलब बाहर लेनी है कहीं तो फिर मैं अभी क्लास में हूँ, तो क्लास के बाद मैं आपके पास आता हूँ। अगर बाहर यहाँ कॉलेज में किसी में लेनी है, ठीक है? आप डिसाइड कर लो, फिर मुझे फोन करना। ओके, सो nitrogen is sp2 hybridized and phosphorus is sp3 hybridized. So 2pz orbital of the nitrogen overlaps sidewise. Now there some people say that this is partially occupied nitrogen atom. I mean, the 2s orbital has been one of the electrons from the 2s orbital. This is 2pz of the nitrogen atom is partially occupied, having a single electron, and 3d orbitals have the one of the electrons from s orbital of the phosphorus has been promoted to the d orbital, and then phosphorus has 5 unpaired electrons, and therefore there is regular or covalent bonding between d orbital and p orbitals of the nitrogen phosphorus atoms, but involving 3 atoms simultaneously, using, because we don't have a pz orbital type situation where we have in the benzene every carbon atom having a pz orbital in the same orientation perpendicular to the benzene ring, and therefore there is a sidewise overlap between p orbitals. That situation is not here. We do have, every atom has an orbital, but then orientation is also important, that the p has pz orbital, the nitrogen has pz orbital, the phosphorus atoms don't have pz orbital available. They have used they have to use the d orbitals, and the orientation of the d orbitals is important apart from the size. So unlike benzene and borazine, delocalization of the pi overlap is not complete. This is not a complete delocalization of the pi bonds, which happens in the borazine or which happens in the benzene. This is partial delocalization, and therefore it has its own consequences in the sense that the phosphazenes are not so aromatic. The aromaticity is not so high, is not, the resonance energy is not so high as is in the benzene ring, and therefore it is not so resistant towards reaction as is the benzene. In benzene, it's very difficult to substitute hydrogen atom. If you don't use the catalyst and harsh conditions, the reaction doesn't proceed. But in the case of phosphazenes, this substitution reaction is quite easy. So the reason is that the delocalization is not complete. The substitution of the side groups leads to 3 types of products. This is the 2 chloro groups replaced on same phosphorus atom. This is called geminal or gem, di-substituted product. And if 2 R groups are replaced from 2 phosphorus atoms and they are on the same side of the ring, we call them cis. If they are on the opposite side of the ring, we call them trans. So we have cis and trans isomers in di-substituted product, or we have gem di-substituted product. So the next is phosphazene polymers. When they are cross-linked, they are similar to rubber in terms of their elasticity, in terms of their stability, and they sometimes they become as hard as plastic also. So they have multiple applications due to they are waterproof, they are fireproof, they are stable at low temperature, and they're also stable at high temperature, unaffected by solvents, oils, or petrol. So they are excellent elastomers used in O-rings and rotor seals for helicopters, which fly at extremely low temperatures. There are biomedical applications, as I said earlier, because of the high structural integrity combined with the biodegradability. So these are the 2 important attributes by which they find application in biomedical applications, because they are biodegradable also, and then they have structural integrity. They maintain their structures in different situations. So if you have a O-ring, it is the flexible, phosphazine, it will remain flexible under extreme conditions. If it is hard, it will maintain its structural integrity under the different conditions. So that property of elasticity is extremely. They're not so cheap that they can use them, and everybody can use them. At the moment, they are very costly products, but maybe their cost will come down. Hello, आदाब जी. हाँ हाँ, कौन जनाब? हाँ कृष्ण जी, वो आपकी बेटी का फोन आया था, मैं अभी क्लास में हूँ, तो वो उसका एडमिशन लॉ में लेना था, तो उनके पास वो कह रही है सीट खत्म हो। एक्चुअली क्या है कि डिफरेंट मेरिट के बच्चों को डिफरेंट दिन बुलाते हैं ना। जैसे हमारे यहाँ भी आज है, हमने आज 70% तक वालों को बुलाया। अगर आज कोई सीट खाली रहेगी तो उसको फिर 65 से 70 वालों को कल बुलाएंगे। इसी तरह उन्होंने भी किया होगा। उनकी ओपन सीट अपने डिपार्टमेंट में कल ही फिलअप हुई है, तो अब वो कह रहे हैं बाहर अगर किसी कॉलेज में लेनी है तो वो उसको मिल सकती है आज। उसमें मैं भी कुछ नहीं कर सकता, क्योंकि ये बड़ा साफ और वो ट्रांसपेरेंट सिस्टम है ना। ठीक है, मैं क्लास के बाद, मैंने बोला उसको, लड़की को दोबारा मैं कॉल करूंगा, पूछूंगा उससे, क्लास में हूँ अभी है। ठीक है, हाँ भेज रहे हो सैंपल पे। मैं सोच रहा था यहाँ फिजिक्स वालों को ही बोले, तो उनको कोई भरोसा ही नहीं है। वो कितनी देर में भेजेंगे? नहीं, वहाँ कितनी देर में होता है? ठीक है, पिछले हफ्ते ही भेजा होता है। तो ये पोस्ट क्या करो ना? हाँ? अच्छा अच्छा, ठीक है। ठीक है, so that is all about the phosphazenes. Yes, and if there are any questions we can discuss. किसी को कोई सवाल पूछना है? हेलो, आप, मेरी आवाज आ रही है?
जी सर।
यस सर।
ओके, आज इतना ही है। मुझे मीटिंग में जाना है, तो 2-4 मिनट अभी, अगर किसी को कोई सवाल पूछना है तो बोलिए। हेलो, हेलो हरजीत कौर, हरजीत कौर, हरजीत कौर, उमेश्वरी सनियाल।
यस सर।
हाँ, आपको मेरी आवाज आ रही है?
यस सर।
हाँ ठीक है, कोई सवाल पूछना है आपने, पूछो।
यस सर।
हाँ बोले। हेलो।
हेलो यस सर।
हाँ हाँ बोलिए। हाँ मुसरत, मुसरत।
यस सर।
हाँ ठीक हो?
यस सर।
हाँ, कोई सवाल पूछना है आपने?
नो सर।
ठीक है, फिर मैं लॉग आउट कर लूँ।
ओके सर, थैंक यू सर।
ओके बाय।